This is geometry lesson 14.5, angles formed by tangents. So, big idea says the measures of angles formed by tangents to circles are extensions of the measures of angles formed by secants. So, these rules that these new lines, tangents, will follow are going to be very similar to what we just looked at with secants. So, this should be nice and easy. So, first of all, let's talk about what is a tangent. So, the definition of a tangent: a line tangent to a circle is a line in the plane of the circle that intersects the circle in exactly one point. Okay, and that is called the point of tangency. So you can see a secant. Remember, we drew a secant. It went through a circle and hit the outside twice. That was a secant. A tangent will hit just once, so just on the edge. One special property of tangents is that if you draw the radius of the circle directly to the point where the tangent touches the circle, they will hit at 90 degrees. So you will see that kind of question pop up from time to time. So the radius will hit a tangent at 90 degrees. So far, quick review of what we did in 14.3. We've learned three theorems with measures of angles and areas. Our angle chord theorem: if we have two lines, whether they're secants or chords, and they're crossing in the middle of the circle, we have those two intersected arcs. We add them together and divide by 2, which is the mean. We average them together, and that creates that angle that's on the inside. Sometimes we have that point of intersection on the edge of the circle, and that's our inscribed angle. And so that angle is just half the size of the one arc that it's creating. So you take the arc and divide it by 2. And then when that angle is on the outside, we take the two arcs and we subtract the big one minus the small one and then divide it by 2. And so we're going to see very similar things here with tangents. So these three theorems don't cover situations in when we have a tangent line. And so those three cases appear below. So sometimes we can have a tangent that hits another line on the edge of a circle. We can have a tangent that hits a secant on the outside, and we can have another intersection on the outside that's tangent to tangent. Okay, so tangent going this way, tangent going this way. So on this one, we have one arc that's created, and that's similar to an inscribed angle, and the theorem is going to match it. We'll look at that in a second. Our tangent secant, so we've got that angle out here. It's creating, again, similar to the one up here, two arcs, and we will handle it very similarly. And then our tangent to tangent, we've got the same situation. We've got two arcs. Now, these two arcs in this case cover the entire circle, and so they will equal 360 degrees on this case when you add them together. You can see here they wouldn't add up to 360 because we do have part of the circle unaccounted for. But when we have a tangent to tangent case, all right, you've got half, well, not half, but one part of the circle on one side and then all of the rest of the circle on the other. So together, those two arcs will add up to 360. All right, so the tangent chord theorem. So this is going to be looking at this first situation. The point of intersection is on the outside, just like an inscribed angle. So right here, this is an inscribed angle, right? We don't have a tangent here. Both of these are hitting twice. This is just an inscribed angle. We know that if we take half of 128.2, we get this angle in here. So if I was going to write this out, the measure of angle A is always going to be equal to half of the arc. So half of the arc measure of arc BC. Okay, that's the inscribed angle. And so here now you see we have a tangent. This line is just hitting the circle once. Then we have a secant here, but their point of intersection is on the edge of the circle. So depending on which angle we're looking at, okay, they only have one arc that they are creating on the inside of that angle. So I'm going to add some letters here. I'm going to add a D out here. Go ahead and add this in your picture. I'm going to add an X here, and I'm going to add a Y over here. And that's just so that we can write this out to label it properly. So I've got this angle in here. Okay, so we're going to call that the measure of angle CAB. CAB. That angle in there, inside that angle, there's just this one arc, right? We've got this one arc in here. So because it's on the edge of a circle, it's just like your inscribed angles. This is just going to be equal to 1/2 the arc. If you take half of 229.8, you're going to get 114.9. Or if you times this by 2, you're going to get the measure of that arc. So it's going to be equal to 1/2 the measure of, and we're going to call this arc AYB. Now the same thing is going to be true on the other side here. So I've got this angle in here. That would be the measure of angle DAB. Okay, and that has one arc inside of it. And so this angle is going to be equal to half of the arc. So if I took half of the 130.2, I'm going to get the 65.1 that's in here. So it's 1/2 of the measure of this arc, and we're going to call that AXB. All right, so if you have a tangent hitting a secant on the edge of a circle, it works just like an inscribed angle, nice and easy. To the back. All right, so what happens when we have these intersections on the outside? So the tangent secant theorem. So the measure of the angle between two tangents or between a tangent and a secant is half the difference of the intercepted arc. So notice this covers two tangents. So whether it's going to the outside twice, which we see down here, okay, a tangent and a tangent, or like we have here, we have a tangent right here, it's hitting the circle once, and we have a secant right here, it's hitting it twice. It's going to follow the same rules as two secants that have an intersection on the outside as well. That angle, angle E, is going to be half of these angles, or these arcs, I should say, subtracted. So you have an arc created here, and you have an arc created here. When the angle's on the outside, you subtract the value or the measure of those arcs and take half, and it will give you the angle in there. So let's try one of these out. Example number 1. Use the figure at the right. AB is a tangent. Find the measure of angle A. So we're trying to find this right here. So the measure of angle A is going to equal, so that angle's on the outside. That means I'm subtracting these arcs and taking half. So I'm going to take the measure of arc B, I'll let the bigger one first, BD, and I'm going to subtract the measure of BC, and then I'm going to take half. Okay, subtract your arcs, take half. Now currently, I don't have the measure of this right here, but I do have the rest of the circle currently. I've got the 73 and the 157. I know altogether this is going to have to equal 360. So I'm going to do 360 and I'm going to subtract away the 73. I'm going to subtract away the 157. And that leaves me with 130 degrees. Okay, so I know that this is 130 degrees. Okay, so now I have enough information to do this. I'm going to subtract my arcs, divide by 2, and I will get the measure of my angle. So angle A is equal to 130 minus 73 divided by 2. That comes out to 57 over 2. Make sure if you're putting this all in your calculator at once, you use parentheses up here. Otherwise, subtract first, get your answer, and then divide. So angle A equals 28.5 degrees. All right, so if you were feeling good in 14.3, this will be no problem for you at all. So special case, or something special to look at, what happens when we have two tangents? We know they're going to add up to 360 because they complete the circle. We also know that you can subtract them and divide by 2 to get that angle, just like we did up here. So if I'm just given my angle out here, I can set up an equation using x to find both of these because they have that special relationship where they add up to 360. So pretend that the x and the 360 minus x were not sitting there for you. You could still put them in there, and that's what we're going to look at here. Just given the 40 degrees, we're going to call this x. That's what we're looking for. They want you to find QSR. We're going to call that x. And we know the rest of the circle would be 360 minus whatever this is. So I can call this 360 minus x. I have enough information to actually find out these arcs now. So if I set up my equation, my angle, which is 40, is going to equal this arc minus this arc divided by 2. So the big arc is 360 minus x. The little one is x. So I'm taking the big arc minus the little arc and dividing by 2. If I run this algebra, I can actually get the value of x here. So with just one piece of information on these tangents, I can actually find everything. I'm going to times by 2 first to clear out my 1/2 or my divide by 2. So I'm going to have 80 equals 360 minus x minus x. I'm going to go ahead and drop the parentheses there. That would simplify. That's a negative x and a negative x. That's going to be a negative 2x. Okay, I'll bring everything else down here. At that point, I want to get x by itself, so I'm going to go ahead and minus 360. Now that's going to get me a negative over there, right? We know we don't have negative arcs, negative angles, but this minus will stay with the 2. So I'm going to end up dividing by a negative, which will make things work out in the end. So 80 minus 360 is negative 280. Bring the whole thing down, negative 2x. You would divide by negative 2. The negatives would cancel. This, of course, would cancel, and x is 140 degrees. So I know that this arc in here is 140, and if I wanted to find the other arc, I would just do 360 minus 140, and I could get that as well.